Okay, we're picking up right where we left off from the previous video, going through the Taylor and Maclaurin series section. Okay, so if we come down here, where we're currently at is we have a function that we want to represent as a power series. This function is f of x. And so the only way you can do this, the only way you can represent a function as a power series is by doing a Taylor series. Now, the first thing you do is you pick what the center point of the power series is going to be. You're going to represent your function as a series, but centered at a certain point. So you pick the center point. If the center point is 0, that's called a Maclaurin series. And in order to make this work, the first criteria that needs to be passed is you have to actually mechanically be able to represent the function as the Taylor series. In other words, there needs to be an unlimited number of derivatives. And then once you take any of these derivatives, there can't be an issue with some of the end terms where like there's a domain issue or something. You're dividing by 0 or something like that. So an unlimited number of derivatives, and then any of the corresponding, coefficients in terms in the infinite series, there's no issues. So that's the first criteria, that you can actually go from f of x, but not equal to, but you can just write a Taylor series for the function. But then the second criteria is we need to actually prove that f of x is equal to its Taylor series. And to do that, the first thing we did was we introduced the idea of the partial sum of a Taylor series. So we already knew what partial sums were. We know what a partial sum is of an infinite series. But this is the first time in this chapter that we've thought about the idea of a partial sum with like an x variable in the series. So with power series, we haven't really thought about the partial sum of a power series yet. So, just like with regular partial sums that didn't have x's, it was like you had s of n, but then if it was the infinite series, you just put s. It's the same idea here. You have t of x and t sub n of x, okay? And it's just what you would think it is. It's instead of doing n going to infinity, you pick n is equal to 10 or 50 or whatever, and for as long as it's convergent and you pick an x value that's convergent, you can get like not the infinite sum, but the partial sum of the Taylor series. Okay, so then with that, what we said was, okay, we're trying to show that f of x, the function, is equal to the limit as n approaches infinity of the partial sum. That's another way of looking at an infinite sum. You can think about the limit as n goes to infinity of the s of n, right? That's just another way of defining an infinite sum. So we want to look at it through this perspective. And again, with this notation here, they don't put x minus a, like it looks like it's common convention when you do like a Taylor series like this, you don't have to put the center point. They're not putting it here, but I just want to note we've chosen a center point. So if we would choose another center point, we have to redo all of this all over again. Okay, so we've chosen a center point, and we've chosen a center point, and we've shown that we can the function has a Taylor series. Like there's no issues with the infinite derivatives or anything. We've chosen a center point. We have the Taylor series, t of x, and then if we have that, then we can get t sub n of x, no problem, right? But so f of x, we want to show this, that f of x is equal to the limit as n approaches infinity of t sub n of x. Okay, well, with partial sums, we know every partial sum has a corresponding r sub n associated with the partial sum, right? We know what r sub n means. So let's think about the r sub n of the Taylor series. And it's r sub n of x. And this is a little, don't let yourself get confused, because this is the first time you've seen an r sub n of x. So just note that. We've done a lot of work with r sub n, but never up to this point with r sub n of x. Okay, so we know what r sub n is, though. It's the infinite sum is equal to the t sub n plus the r sub n. And then you can think about the x is like, so at the center point, r sub n is going to be 0, because the way the Taylor series is set up, and also t sub n, that's the Taylor polynomial. We call it the Taylor polynomial. This is the Taylor series, this is the Taylor polynomial. But the way that the Taylor series is set up is that it's actually literally on the function at the center point. But everything else away from the center point is an approximation. And so you can think about the r sub n is going to depend on x. The error depends on both n. The larger the n you use, the better, the smaller r sub n is going to be. But then also at the same time, if you pick an x really far from the center point, the error is going to be larger in that case. So the r sub n here is a function. There's two variables that are at play here. Okay, so since f of x, which is the infinite series, we're assuming that f of x is equal to the infinite series. If that's the case, then the infinite series, since the infinite series is equal to t sub n plus r sub n, then you can subtract t sub n from both sides and get this. Okay, and then, well, okay, yeah, so they were just creating this formula. The infinite series, which we're assuming is f of x, we're trying to prove this, that this is true. If it's true, then this is the case. The infinite series, which is f of x, is equal to the t sub n of x plus the r sub n of x. R sub n of x is called the remainder of the Taylor series. And so we need to prove this, but this looks difficult, right? We need to take the limit as n approaches infinity of the power series, the partial sum power series, and get a function of x. That seems difficult. Well, that's not what we're going to do, though. We're going to actually go another route to where if we can show that the limit as n approaches infinity of r sub n of x is equal to 0, this is easier to work with. We don't have to say that the limit as n approaches infinity of some partial sum of x formula is equal to another function. We have to just show it's equal to 0. If we can show this, then we've proven that f of x equals the Taylor series. And they show why that is here. You can see why that is here. Okay, and so this theorem just states what I just said. If you have a t sub n of x and an r sub n of x, where t sub n is the nth degree Taylor polynomial and of f. So just because f is not equal to the Taylor series or to the t sub n doesn't mean that it doesn't have a Taylor series representation. So it's saying where t sub n is the nth degree Taylor polynomial of f. So we haven't shown they're equal yet. It's just the nth degree Taylor polynomial of f at a center point. It has to be at a certain center point. But if you show this, though, if you show that the corresponding r sub n of x, as n goes to infinity, that's equal to 0, then it must mean that f of x is equal to t of x. And that makes sense why that is, but you might be scratching your head thinking that, yeah, that's true, but the tricky part here is how do we get, what's r sub n of x? Because the key to making this work is you have to know what r sub n of x is. It has to be related to the f of x, right? Because the idea is you can have an f of x and you can associate with it a t sub n of x. But this remainder here is the difference between the t sub n of x and the function itself. So to make this work, we need to get, how do we get r sub n of x so that it has that intimate tie to f of x? Well, that's what Taylor's inequality is all about. Taylor's inequality is going to give us an upper bound on r sub n of x. Okay, so if we come here, Taylor's inequality is, it's all about, it's giving you an upper bound on this r sub n of x. And it says absolute value here because, you know, the error could be positive or negative. It's just giving you an upper bound on the r sub n of x. That is Taylor's inequality. And below this, it gives the proof of this. And the f of x being tied in comes in right here. I'll talk about that in a second. They give the proof of this below. We're not going to get into the proof. And so since we're not looking at the proof, you're just going to look at this as just kind of a random formula that you know is true. So you don't need to memorize this. You could just either come to your textbook when you need it or Google it. But what you need to memorize is what it's giving you. What the Taylor's inequality is giving you an upper bound on the r sub n of x, the remainder of a Taylor series associated with the Taylor polynomial. That's what it's giving you. Okay, and so with that, you can think about here in this video, we're going to be using this r sub n to prove that an f of x is equal to its Taylor series. But in the next section, there's going to be another way we're going to use this, Taylor's inequality. And that's going to be because for exactly what we were doing with r sub n in the previous sections. We were using r sub n to get error estimates on partial sums of series. So in the next section, we're going to talk about using Taylor polynomials to get estimates for function representations as series, and the Taylor's inequality is going to give us allow us to quantify the accuracy of that estimate. But again, here, that's not what we're using Taylor's inequality for. Here, we're using Taylor's inequality to get the R sub n of x and use that to take the limit as n approaches infinity of R sub n to prove that f of x is equal to its Taylor series. Okay, so now let me walk you through this inequality. I'm going to actually start by, let's go through the main inequality here that gives you the upper bound on R sub n. So again, it's the absolute value, because it could be positive or negative. It's less than or equal to this is just a number, m, some number, divided by n plus 1 factorial. So n is it's the number you choose for the Taylor polynomial. Maybe you want to sum the first 10 terms. That's accurate enough. It's whatever that you're going to put in a t sub n. That's n. And then, so n plus 1 factorial, and then times the absolute value of x minus a to the n plus 1. All right, it's the absolute value because you could choose an x that's above or below the center point. And the R sub n, again, is going to depend on how far away. You can see the farther away you are from the center point, depending on the x you pick, then the larger, the upper bound is going to be larger. On R sub n is going to be bigger. But if you pick the center point, then it's the error is 0. Because this is the absolute value. So this is going to be, right? Since it's absolute value here, then this is never going to be less than 0. So if you put the center point, then it's 0. The error is 0. But again, it's the absolute value because x could be above or below a. Now, it says here for the distance from a, the absolute value of the distance from a is less than or equal to d. We're used to seeing r here, right? The valid inputs into the Taylor series, for example, are a certain distance r to the left or right of the center point. But this is d, so what does this mean? Well, you can think about d as like the equivalent of r, but not in the sense that it gives the valid inputs into the power series or the Taylor series, the convergent inputs, but in the sense that it specifies the inputs that pass Taylor's inequality. So that mean that this is valid. So the values of x that to where this inequality holds. Right, we're going to see all of this. The criteria for this inequality doesn't really have anything to do with series convergence. So this d is just like another radius associated with Taylor's inequality. And so if you think about it, before you've even proven that f of x is equal to its Taylor series, you've still already solved for what the radius of convergence of the Taylor series is. So prior to Taylor's inequality, you already have an r value for the Taylor series. So when you come to Taylor's inequality, maybe it's the case that d ends up being less than r. And so in that case, you can think about that kind of restricts, technically it doesn't restrict the interval of convergence of the Taylor polynomial, but you can only use R sub n for the proof that f of x is equal to the Taylor series, or for the error approximation of the Taylor series for a restricted r. It restricts the r in that case down to whatever d is. So to prove that f of x is equal to the Taylor series, you might have to use go to another method for the rest of the radius of convergence. Or maybe d is equal to r, or maybe d is greater than r, which for the extra values that are greater than r, this doesn't apply anyway, because there wouldn't, if it's not within the interval of convergence of the actual series, then r sub n of x doesn't exist in that case anyway, because there's no infinite sum value. And they don't actually mention it in the textbook, but I'm not sure if there's like other proofs in other math books, more advanced math books, that prove that d could actually never be greater than r. I'm thinking it could be, but I'm just trying to give you a sense of what they're talking about with d here. So how does it work that only certain radiuses around the center point could be applicable for Taylor's inequality? What does that mean? Well, let's see where does capital M come from? Because we know we choose n, we choose a. Here's n. So the only thing we're left with is what is this capital M? Well, okay, that's here. It's the absolute value of the n plus 1th derivative of the function. Okay, so remember, you start with a function like e to the x or sine of x, and you choose a center point, but you don't it's not like you choose a center point and now you change your function to e to the x minus 2 if you chose the center point to be 2. You don't do that. No, it's always it's going to be, you're saying e to the x or sine of x, etc., just the function itself, and then the center point's going to come in the power series. The function itself is always just the function. So like if you're approximating e to the x at center point equal to 0, it's going to be e to the x is approximately equal to something. If you're approximating e to the x at a center point of 2, it's just going to be e to the x is equal to something else. So just keep that in mind. The center point does not have anything to do with like the function itself, okay? So, but you've got the function you're approximating. It's got like an unlimited number of derivatives. What they're saying here is that you take the n plus 1th. So it depends on if you're going to do the Taylor polynomial to n is equal to 10, then you're going to take the 11th derivative of the function. And it's going to be like e to the x. The 11th derivative of e to the x is e to the x. It's going to be a function of x. Okay, you think about that as an absolute value, the absolute value of that function. If that's less than or equal to some m value, okay, for some radial distance about the center point, if that criteria is satisfied, then you can go ahead and use Taylor's inequality. Okay, and so again, the d, this is variable. And so it's variable in the sense that maybe, all right, let's use e to the x as an example. The 11th derivative of e to the x is just e to the x. Any derivative of e to the x is just e to the x, okay? There's e to the x, something like that. Your center point, maybe it's at 0, maybe it's at 2, maybe it's at negative 2. Your center point somewhere. Let's say it was at 1. There's the center point. Okay, it's saying that if you plug in an x that's away from 1 in the positive or negative direction, is the absolute value of that, and the absolute value doesn't matter here, this is always positive, is the absolute value of what you get after when you plug in that x value, is that less than or equal to some finite number? If it is, then you can apply Taylor's inequality. So if we think about that here, so if we plugged in like x, this x, that'd be x is equal to 3. We get e to the 3. Okay, now we think about, we chose x is equal to 3. So 3 minus 1 is 2. So the distance from the center point is less than or equal to 2. So we could go from 3 to it would be minus 2. That's plus or minus 3 from the center point. Okay? So over this entire radius, this distance that'd be plus or minus 2 from A. For any x in that radius, is the n plus 1th derivative for any of those x's, is there some number m that's less than or equal to any of those values? Well, all of these, you could pick anything, and it satisfies the criteria. And actually, to make it simple, what you would do is say, instead of saying like e cubed, you could just say that this works for, you could pick any d you want. For this function, you could do this. You could pick any d. And so this would be, over here would be not minus d, it would be, minus d plus 1. But in that case, the number would be m would be e to the d power. So this criteria is satisfied for any number d. Now, it's not saying that d can be infinity. They're talking about specific numbers here. Because like m, this is we're thinking about finite numbers. But any finite number d, it's going to be a positive number, it's absolute value, then this criteria is satisfied. That means at least at this center, we're talking about just this one center point here, but you can see with e to the x, you could choose any center point and this would work. But we're thinking about one center point function at a time. But for the specific center point, for any number d, this is true. So that means Taylor's inequality holds. Now you can see with other types of functions, it can get even simpler, like sine of x or cosine of x. The n plus 1th derivative, when you plug in x, it's bounded above by positive 1. So it's not even like a formula. You don't even have to make m a function of d. You could just actually put the number 1, which makes it even simpler. But there could be other functions where it doesn't work for just any value of d. It's only for like a certain, up to a certain d value. You know, maybe it's, I don't know, something like that, and you're trying to approximate the function here, and you can only go up to, it's only when you get here. So you'd be plus or minus, so you'd be equidistant on the other side. You know, so you could only, this Taylor's inequality would only be valid up to this distance d away from the center. That's the center. And so, you know, it might seem like kind of, it's so simple. It seems like sometimes things are so simple that this inequality is so complicated, but this criteria for the uppercase M is so simple. Yeah, it is. I mean, literally here, you know, we worked in chapter 4 finding the global maximum on an interval. That's what you're doing. You're picking a d value, and then that creates your plus or minus d from the center point. And the criteria is there a finite global max on that interval, where you plug in any x value into the n plus 1th derivative of the function. It's not, you know, e to the x, it actually is the original function, but in a lot of cases, that's not actually the original function, it's the n plus 1th derivative. You can plug in any x value, and no matter what x value you plug in, there is a finite number that's greater than or equal to any of any of those values. Okay. So they give a proof of Taylor's inequality here. We're not going to go through this. Okay, they note here that in the next section, we're going to be using Taylor's inequality for error estimations on Taylor polynomials. But right now, we're using it for a different purpose. So, okay, we're going to apply, now we're going to apply the R sub n estimation and to actually prove that a function is equal to its Taylor series. So we're going to take the limit as n goes to infinity of the R sub n and show that that's equal to 0. So it says to do this, we want to make use of this limit here. The limit as n approaches infinity of x to the n over n factorial is equal to 0 for every number x. Okay, now just quickly, how did they determine that this limit was, how could you determine this limit? Well, okay, we just dealt with this. This was the power, this was the a sub n for the power series representation of e to the x centered at 0. If we come back to that, right, so this is the Maclaurin series of e to the x, and it was this here. And we did the ratio test and found that it was convergent for all x, all real numbers. Well, okay, with that, let's think about the test for divergence. If this series is convergent for all x, if it's convergent, then the a sub n, the limit of the a sub n has to be equal to 0. That's like a fact for convergent series. If it was like the other way around, let's say this series were hypothetically divergent for all x, then we couldn't go to the test for divergence and get like what its limit is, because its limit could be anything other than 0. But if it's the case where the series is convergent for all x, or even it could be specific x, then if it was just a specific x's, we know the limit for specific x's. But okay, it's convergent for all x, so we know the limit of the a sub n is 0 for all x. It must be. Okay, so let's take note that this limit here is equal to 0. You have to use this limit for a lot of the proofs that f of x is equal to its Taylor series. Okay, so let's prove that e to the x is equal to the sum of its Maclaurin series. So again, let's come back. We did the Maclaurin series representation of e to the x here to represent any function as a power series, to find its power series representation, not just the Maclaurin series, but centered anywhere. We make 2 columns and put like the first 4 or 5 derivatives of the function. It doesn't matter where we're centered at. It's just the function of x until you can like see a pattern. And then you go to the other side and you plug in the center point into the function and kind of see the corresponding pattern of actual numbers. Because once you plug in a value for x, the function evaluates to a number, right? Like the function disappears because you're actually plugging in a value. It's like, you know, natural log of something. Once you plug in something, usually, not always, but typically a lot of times the function goes away, okay? And you want to look for a pattern because ideally you're taking the, so it's the nth derivative of the center point is what you're looking at here. You're looking at the first 4, 5, 6 derivatives, then you're plugging in the center point, and to see if you have a pattern for the nth derivative at the center point. So it's the nth derivative at the center point divided by n factorial times x to the n. Because since a is equal to 0, this is the center point 0, a is equal to 0, so it's just x to the n. And since e to the 0 is always 1, you just end up with x to the n over n factorial. So there's the Maclaurin series of e to the x. So we want to prove that e to the x is equal to the sum of its Maclaurin series. We want to prove that e to the x is exactly equal to sum from e is equal to 0 to infinity. Because of the infinity, it's exact, of x to the n over n factorial. Okay, so they say they think about the n plus 1th derivative of the function. It's going to be e to the x for all n. So if d is any positive number and the absolute value of x minus a is 0, is less than or equal to d, then the n plus 1th derivative evaluated at x is equal to e to the x, and that's going to be less than or equal to e to the d. Right? That's what we just talked about. M is going to be equal to e to the d, which means that if you pick any number d, and that's going to be a radius centered about the center point. That's a d is a number that represents the radius about the center point, plus or minus from the center point. If you evaluate the n plus 1th derivative at any x within that interval, including the endpoints, then every single resulting value is, no matter what you choose, is going to be less than or equal to e to the d. And so that satisfies Taylor's inequality. In this case, with a is equal to 0 and m is equal to e to the d. So you can write that you can write out Taylor's inequality and just put what the m is. This is e to the d. Everything else is just like, here's the n values and the x. And then you can just put d here. Okay, it says, notice that the same constant, capital M is equal to e to the d, works for every value of n. And this mainly comes from the fact that the n plus 1th derivative of e to the x is always the same thing. The value of n comes in with the n plus 1th derivative. But from equation 10 we have, so equation 10 is the limit as n goes to infinity of x to the n over n factorial. That's equation 10. And so they're taking this limit, and you could bring, d is not a function of n, so you can take the e to the d out of the limit. And this is, that now we're taking this limit, which is similar enough to equation 10. It's x to the n, the absolute value of x to the n plus 1 over n plus 1 factorial, but at infinity, the plus 1 is negligible. You just make this n factorial, and same here. So this is effectively, when n goes to infinity, this is effectively the same thing as the limit as n goes to infinity of the absolute value of x to the n over n factorial. And that's going to be equal to 0. And you might be saying, well, what about the absolute value, though? That's not the same as this. Well, okay, yeah, the absolute value could come into play, but it doesn't, because, like, okay, if x is negative, then you're going to be approaching 0. Like, I guess it would be oscillating. If x is negative, you'd be oscillating positive and negative signs. But it's like, either you could think about it, you're either approaching 0 from the bottom or the top. But regardless, it doesn't matter anyway. The number is, no matter what x is, this number is shrinking to a tiny number in magnitude, this entire ratio. So this limit is equal to 0. And so it says, with that, from the squeeze theorem, we say that the limit as n approaches infinity of the absolute value of r sub n of x is equal to 0. So what are they talking about here? Well, remember this is the absolute value of r sub n of x, so that can't be less than 0. So it's the squeeze theorem. You know that a function is less than or equal to some other function and greater than or equal to some other function if you show that the limit as n approaches infinity of the upper function goes to a number like 0, and then you show the limit approaches infinity of the other side goes to 0, the limit as n approaches infinity of 0 is 0, then you know what this limit must be 0. In other words, the limit as n approaches infinity of the absolute value of r sub n of x is equal to 0. Okay, and so that means that e to the x is equal to the sum of its Maclaurin series. That means that you've proven that e to the x is equal to this for all x. You've officially proven it. Now, you might be a little confused thinking that, well, what about the d here? Like if you think about, okay, as d goes to infinity, you end up with kind of a infinity times 0. That's indeterminate. Well, no, okay, we don't think about d going to infinity, right? D is just representative of the number you're going to be plugging in for x. So this is satisfied if you might pick a really large number. You could pick d is equal to 10 billion, but if you pick a number, a specific number, then this is 0. Because you have e to the d, a specific number, times something that's infinitesimally close to 0. Okay, so now they plug in x is equal to 1, and they get the infinite series representation for the number e. Pretty cool. E itself is literally equal to this as an infinite series. And you can think about why that's pretty cool because, yeah, we represented repeating decimals as infinite series earlier in the chapter, but e is not a repeating decimal, but we still have an infinite series representation for it. Okay, we'll continue with this section in the next video.